Hello. Today I'm going to be talking about undamped oscillators, underdamped oscillators, critically damped, and overdamped oscillators. Now this is a really important topic in engineering and science because we love oscillators. They make the world go round. All right. So we have two models here. There's a mass on a spring, a mechanical oscillator. And we got an electrical oscillator, an LRC circuit. Okay. I want to talk a little bit about the parameters. Mass is positive, and that's the MA term. Friction constant gamma could be 0 or it's positive. In real life, it's never 0, but in our models it can. And K, the spring constant, is positive. Then the inductance is positive, the resistance is greater than or equal to 0, and the capacitance is positive. Okay, so I'm going to mainly talk about this left model, and I want to try to understand what happens for every M, every gamma, and every K, and that's a lot. In fact, in every initial condition as well. So there's been a big task ahead of us. So the first thing we do is, even though it looks like there's 3 parameters in gamma and K, we just divide through by M and get y double prime plus gamma over M y prime plus K over M y equals 0. So we really only have two parameters essentially. And let's remember that we define let omega naught be square root of K over M. So this is just omega naught squared y. And remember, omega naught is the frequency of the undamped system, but we still talk about omega naught a lot, even if you have damping. All right, so that's not going to change, but here, what are we going to do with this gamma over M? I'm going to write this is gamma over M times, let's put in an omega naught here, K over M. What I've done here is I put in a form of 1. And why did I do that? Well, because that way, if I write this as y double prime, gather these together, and I get the square root of M over M is 1 over square root of M. This is gamma over square root of MK. And then this part is omega naught, right? That's omega naught y prime plus omega naught squared y equals 0. Now, the nice thing about this is that this is a dimensionless constant that measures the friction or the damping. One way to see that is that every term here has units of meters per second squared. Y has units of meters, and so the second derivative of the acceleration is meters per second squared. That's inverse seconds, that's meters per second. Together I get meters per second squared, that's dimensionless. That's inverse seconds squared, that's meters. Okay, so this here is a dimensionless constant, okay? So it has a few different names. I'm going to call this B, and in general, in math, we define this to be something like, I'm going to call this 2C. In engineering, we would probably call this 1 over Q, is this gamma over MK. So Q is the quality factor of the oscillator. And you often hear about a high Q oscillator. There are some things where Q, like a high Q oscillators might have 10 to the 11th or something, a really huge Q, a really small C. Okay. So let's, this has units. Omega naught has units, seconds to the -1, and our C, which is gamma, well, let's make a nice gamma, over 2 square root of MK is unitless. Or I can define Q, which is 1 over 2C. You wouldn't want to use C and Q. You can choose one or the other. And I'm going to be focusing on the C. Okay. And you'll see why I put the 2 in there. The formulas are a little bit nicer. So let's keep that original equation, but rewrite the scale one. Okay, so we've got y double prime plus 2c omega naught y prime plus omega naught squared y equals 0. And then we want to find the characteristic equation for this, etc. So we have r squared plus 2c omega naught r plus omega naught squared is 0. Quadratic formula, r plus or minus is minus b minus 2c omega naught plus or minus square root of b squared 2c omega naught all squared minus 4 times a, which is 1, times c, which is omega naught squared, all over 2a. But a is 1, sorry. All over 2. Okay. So let's cancel the 2's. I get minus c omega naught. And I get plus or minus a half times, what is this thing here? I get 4 c squared omega naught squared minus 4 omega naught squared. Okay, that I can plus or minus a half. I get 2c times, no I don't. I can factor out a 4 omega naught squared. Square root of 4 omega naught squared, all times c squared minus 1. And that's going to be a 2 omega naught. So it's minus c omega naught, plus or minus the 2's cancel, omega naught times square root of c squared minus 1. This is r plus or minus. Cool. All right, okay. So let's think about the various types of roots we get for the different values of c. I'll keep that down there, and hopefully, I think I'll just get rid of everything. So there's 4 cases, 1, 2, 3, 4. So case 1, Roman numerals, is undamped. That's c equals 0. Okay, well the roots r plus or minus are 0 plus or minus omega naught times square root of negative 1. That's I. Okay, that's kind of familiar. We know that the general solution is y is, I'm going to write that nice angle, radius angle formula, cos of omega naught t minus delta. And that looks like a sine or a cosine or some shifted sine or cosine with a constant frequency, okay, and constant amplitude. It never decays. There's t and y. So case 2 is underdamped. This is 0 less than c less than 1, or using q, that's q greater than. Okay. And as I say, sometimes q can be millions and c is really small, but okay. So what we have here, the roots are plus or minus r minus c omega naught. Okay, well, plus or minus I omega naught 1 minus c squared. So when c is small like that, that's a negative number. I switch it and multiply by minus 1. Minus 1 gives it the I, and then I end up switching that. Okay. So the general solution is y is, I'll use a similar kind of form. Here, I multiply the r by a decaying exponential, e to the minus c omega naught t, all times cosine of omega naught times 1 minus c squared, all times t. I guess I don't really need that. But I'm going to actually write it a little bit differently. I'm going to put the omega naught t together. This is 1 minus c squared inside the square root times omega naught t. Okay. All right. So one of the things that happens in this is omega naught t always comes together. It always likes to be together. All right. So this is case 3. This is critically damped. C equals 1. And before I do that, I forgot to draw the pictures of the underdamped. This is a decaying exponential. And then it gets multiplied by something bouncing back and forth between 1 and minus 1. So the picture looks like this. Here's t. I get an envelope that looks like that. Plus or minus r, e to the minus stuff. And then a solution will look something like that. It has a period that's longer than a period here that's longer than 2 pi, because this is a frequency slightly smaller than omega naught. Okay, critically damped, c equals 1, or u is a half, the quality factor. And hopefully I'll remember that one in a minute. Yeah, sure. All right, so here the general solution is y is c1 e to the, I should say what the roots are first. The roots are r plus or minus is minus c omega naught, but c is 1, so it's just minus omega naught. Actually, we saw that in the videos about the LRC circuit. So there's minus omega naught, minus omega naught. So I need a C1 plus C2t. And I might as well write the general solution is C1 plus C2. Heck, let's just throw in that omega naught t. And e to minus omega naught t. So this is another way of writing the general solution, but it preserves the fact that every time I see t, it has an omega naught in front of me. So I could leave that out and I'd have a different constant. Okay, so then we have case 4. This is, what is it? Overdamped. This is c greater than 1. And if I do that with q, this is q less than a half. All right. So here we have the roots r plus or minus is minus c omega naught. I think it's like that. Plus or minus square root. Actually, I can do the same thing. I can write this as omega naught times now square root of c squared minus 1. All right. So let's see if I can have room over here to write the general solution. The general solution is going to be y is c1 e to the, let's write this is, notice that this had the factor of the omega naught. This is minus c minus square root of c squared minus 1 omega naught t plus c2 e to the minus c plus square root of c squared minus 1 omega naught t. Okay, so again, everything just depends on omega naught t. And the other thing we can see is that this R, we have R minus less, sorry, R minus less than R plus less than 0. This thing here, R minus is definitely negative, but R plus is also negative because negative C beats out square root of C squared minus 1, right? Because that minus 1 wasn't there, that would be C. But now this is a little bit less than C with the minus 1 there. So, but you notice that R minus is approximately minus 2C. And R plus goes to 0 as C goes to infinity. All right, so that's kind of an important thing here, that one of these roots, this the second one here, that's actually going to 0. So what that means is if C2 is not 0 and the damping is huge, C is big, then this solution will take a long time to decay towards 0. Okay? And in fact, the solutions decay to 0 most quickly with critical damping. Of all of these, this whole thing on the page, critical damping, C equals 1, is the guy that decays to 0 most quickly. Then the other thing about this page you can see is omega naught t always appears together. So in fact, if I plot omega naught t and y, then this picture always looks the same for a solution. The solutions always look the same on this picture, regardless of what omega naught t is. The period might be milliseconds. It might be billions of years, okay? But if I plot it with omega naught t, the picture looks the same, okay, for a given c, okay? All right. So I've got a Desmos graphing calculator example of actually these 4 cases. These are put together because I allow C to be 0. So I have 3 different Desmos calculator graphs that I'm going to share with you. I'm also going to show you a little bit on my, make another little video just demonstrating them a little bit for you. All right. Stay well and keep doing those web work problems. All right, bye.